going to talk about another method for constructing confidence intervals via what's known as the bootstrap. And so the confidence intervals that we have created in the previous class, they rely on distributional assumptions. So basically, we assume a certain distribution of various kind of pieces. For example, we assume that our errors are normally distributed in order to be able to draw the inference that we do from the confidence intervals. But what if we could sort of find a different way to be able to construct these intervals? And so one way to do this is if you could imagine if you knew the true model, so if you knew the true underlying distribution, and you could sample from it, and so you could draw samples from it multiple times, and then you could sort of build a distribution for the different coefficients that you're interested in, for example, for the beta coefficients, and then you could construct a confidence interval from that. That would sort of be another way to go about this. And so what I've just described is what we often in statistics call a simulation. And so the way a simulation would work in the context of least squares or linear regression is we would generate the errors from the known error distribution. So you would basically generate a whole bunch of different errors from the known distribution, and then you'd calculate the y equals x beta plus epsilon, and this would be from a known beta, so you would pull from a known beta, and then you'd use your observed data x to basically be able to calculate this y, so we would have x, beta, and an epsilon, which was drawn from some known distribution. And then from that, we could use our formula for beta hat, the x transpose x inverse x transpose y, to be able to compute beta hat. And so you could do this many times, and you basically, each time you do it, since you're pulling from the known distributions, because this is sort of like similar to if we were sampling from a population many times, we would expect to get slightly different answers every time, but we could use that to sort of construct a distribution of our beta hats, and then we could estimate the uncertainty from that. So this is kind of like an ideal situation or a simulation setting for another way that we could try to construct uncertainty. And I think it sounds great, but the problem is that we actually don't know a lot of pieces that would be necessary to know if we wanted to do this simulation method. So we don't know the true error distribution, and we also don't know the true beta. Womp womp. So this simulation method, while it sounds really good, is actually not feasible when we don't know the truth. And if we did know the truth, then we would just be able to sort of use that. And so that's where bootstrapping comes in. And so the bootstrap basically tries to estimate the same procedure as the simulation method, except instead of sampling from the true distribution, we sample from the observed data. So where does this term bootstrap come from? Well, it comes from the phrase to pull oneself up by one's bootstraps, which likely came from an 18th century writing, The Surprise Adventures of Baron Munchausen. And the quote from this was, "The Baron had fallen to the bottom of a deep lake. Just when it looked like all was lost, he thought to pick himself up by his own bootstraps." So that's the earliest kind of known use of this phrase, or at least what gets propagated in the statistics community as one of the earliest uses of this phrase. But that's where the term bootstrap comes from. Because when we're bootstrapping, we're using the observed data to help us try to estimate this distribution. So we're sort of pulling ourselves up by our own observed data in some sense. And so here's a picture. This is from slides by Hasty and Tibshirani. And this is sort of a picture to try to get at what we're trying to estimate here. So in this part of the picture on the left, we've got a real world setting, and we've got some population, P, and we randomly sample from that population. So this is basically showing kind of what we expect is happening when we're doing statistics. So we have this population P, we randomly sample from this distribution, and we get some data. And so these Z's here are our data. And then we construct some estimate based on that data by taking a function basically of that Z or of that sample. And so this is essentially what we're doing when we're fitting a linear regression model to some data. we are observing this data set Z, which is a sample from the larger population. And the function that we're applying to Z is this linear model. We're fitting this linear regression model, or this least squares model, to that data to construct an estimate. And often the thing that we're interested in is maybe that beta coefficient for that model. Okay, so moving into the Bootstrap world, there are basically analogous sort of between these two. So now in the Bootstrap world, we've got an estimated population, which we can call p hat, and we do some random sampling here, and we get these Z stars. And then we end up estimating this bootstrapped estimate, which is some function of those Z stars. And so this bootstrap data set basically is from a sample from this estimated population. But the estimated population, the way we get that information is all from the observed data by basically doing what's known as resampling from the original observed data to construct new bootstrap data sets. So let's talk a little bit more about exactly precisely how that's done in the least squares case. So this bootstrap is used to estimate uncertainty, for example, the standard error of an estimate or an approximate confidence interval. And so the way we would do this is quite close to the simulation method with some key differences. So if you remember, in the simulation method, we were drawing the error terms epsilon from the known error distribution. Well, in the bootstrap, we're going to generate these E stars, or these errors, by sampling with replacement from the residuals. So from the observed residuals in our data set, E1 to En. And then we're going to calculate this Y star equals X beta hat plus epsilon star. And so this is getting at, basically we're using these new generated error terms that were sampled from the residuals. And then we're going to compute beta hat star from our data X and our new Y star. And this is going to be like this is our estimate, our function of this sampled population that we're interested in. Okay, so this first step, generate E star from sampling with replacement from the residuals. What does that mean? So here I've put together an example where I have a data set with 5 observations, and I fit some model, and I end up with 5 residuals. And so my residuals E that I've observed in this data set are 0.02, 0.02, negative 0.23, 0.42, and negative 0.23. So I've got 5 different potential residuals here. This is my observed data. How would I sample this with replacement? Well, sampling with replacement means that I'm going to randomly draw one of these values at a time, and when I draw it, it doesn't remove it from the potential values to draw. It's just as likely that I could draw it again. So each of these has, when I have 5, each of them has a 1/5 chance of being drawn, and that chance stays the same even if it was already picked. So basically, if you could imagine these 5 residuals all being in a hat, and I yank one out at a time, and I write down what I pulled out, and then I put that residual back in, and then I pull another residual out, I write it down, and then I put that back in. And often you do that the same number of times as observations that you have. So you'll often do that 5 times in this case. And so this is what that could potentially look like. The first time I calculated an E star, I reached into my hat of residuals, and I ended up with 0.02, and then I put that back in, and I ended up with 0.02 again, and I put that back in, I ended up with negative 0.23, put it back in, ended up with negative 0.23 again, put that back in, and ended up with 0.02. And so this is one sample, one bootstrap sample here, and this is an example of sampling with replacement from this original observed residuals data. So this was what I got in my first sample. You'll notice that this 0.42 never showed up in this data set just by chance. That was just never drawn when I was drawing from the hat. And then I do this again. And so the second time, my second sample, I end up pulling negative 0.23, negative 0.23, 0.42, 0.42, and 0.02. And so this time 0.42 was drawn, and in fact it was drawn twice. And so that sort of represents how, because we're sampling with replacement, after I drew it the first time, I put it back in the bag, and it was just as likely that I could draw it a second time. So this is just 5 examples of potential bootstrapped samples that I could draw from this original E, or this original residual. So you sample with replacement many times. From this, we would do this many times so that we can calculate many of these E stars, and subsequently many of the Y stars, and subsequently many of the beta hat stars. So let's do this in R. In R, there's a function called sample that lets you resample with replacement. And so, for example, here, if I want to sample from the vector 1, 2, 3, the first argument of sample is going to be that vector I would like to draw from. And then I'm going to say replace equals true, and that makes sure that we're sampling with replacement. The default here is false, and so by default, it would potentially be a different order than 1, 2, 3, but all of them would end up getting sampled, because once one was drawn, it would go out of the bag. So we want to make sure we do replace equals true so that we are sampling with replacement. So the first time I do this, I end up getting the values 2, 1, 2. If I run this again, I would get a different answer. So the second time I ran this, I ended up with 3, 2, 2. The third time I ended up with 2, 2, 1. And so basically every time I run this, I'll end up with a random pull from this vector here. And so it's really a really important thing when we're doing any kind of random pulling is we want to make sure that we set a seed at the beginning of our random process. And what the seed does is it makes sure that when you, if you run the random process kind of twice with the same seed, you'll get the same answer. And so this makes sure that your results are replicable, that you can replicate those results or reproduce them. And so here I'm setting the seed to 1, and then I run this sample, and I end up with 1, 2, 2. And you'll notice if I run that same code again with that same seed, I get the exact same result, 1, 2, 2. So setting the seed before I run that random process ensures that I'll get the same answer as if I set the seed again and ran the random process again. So it's different than this previous slide where every time I ran it, I ended up with a slightly different random answer. When I set a seed, I always get the same answer. And so, for example, here I've set the seed at the top, and then I've completed 3 random processes, and I end up with 1, 2, 2, 3, 1, 3, and 3, 2, 2. And so if I do this again, if I set that seed again and I run the sample function 3 times, I end up with exactly the same answer. So not only does it affect the very next random process, but it affects kind of all the subsequent random processes as long as they're done in the same order. So anything that's done after the seed is going to give you the same result each time you run the full analysis. So you always want to set a seed when generating a random process so that you can replicate your results. Okay, so let's do a quick application exercise. I want you to first go ahead and open an RMD file, and I want you to set a seed, and then I want you to use the sample function to sample from the following vector with replacement. So I want you to sample from 1, 2, 3, 4, 5. I'm going to give you a couple minutes to work on that. Okay, so go ahead and knit that document and we'll be adding to it later.